Okay, hello everyone. This is the session number 10. Agenda of this session is eigenvalues and eigenvector. This is one of the most important article from the syllabus, eigenvalues and eigenvector. So before we start this topic, you should know the meaning of the word eigen. So eigen is a Latin word. The meaning of eigen is a special. So these are some special values and the special vectors of the matrix. So what is the special thing about these values and the vector? Yes, we'll discuss it. So before that, yes, you can see here one linear transformation. What is this linear transformation? Actually, the equation y is equal to ax is a linear transformation. What happens when you operate the matrix A? When you operate the matrix A on the vector x, okay, indirectly you are multiplying the matrix A with the vector x, so row by column. So you'll observe 2 into 1 is 2 plus 3 is a 5 minus 1 plus 3 is a 2. So what happened in this transformation, in this linear transformation, ax become a y. Ax, the vector x is a transform to the y. Vector x is a transform to the y. So initial vector, if you draw it, so it is 1 comma 3, this is the position, and the new vector is 5 comma 2, this is the new position. What happened? The original vector have this much of magnitude, the new vector have different magnitude. That is the first thing we observed. Second thing, the angle made by that vector with the x-axis is a different, and the angle made by the new vector is a different. Means when we do a linear transformation ax equal to y, what happens generally? The vector x is transformed to the y, and the new vector is generally rotated and it is stretched or scaled, we can say. So it is you can observe the length is different, so it is stretched as well as it is rotated also. It is rotated. So whenever we apply the matrix A, on the vector, generally that vector is stretched and rotated. Now we are interested in some special vectors in special direction, in that direction that rotation is not happening. If rotation is not happening, we say that is a eigenvector. We'll come to that. We'll come to that here. So here is a simple example given. Suppose the matrix A is 1, 2, 2, 4 and the vector x is 1, 2. So if you take A into x here, A into x. So this is A and this is x here. You will get 5 comma 10, 5 10. So if you take 5 common, it is 5 times 1 2. So you'll observe in this case the original vector is 1 2. This is the original vector 1 comma 2, this point, and the new vector is 5 comma 10. So this is the new vector. So the new vector and the original vectors both are on the same line, means the vector x is not rotated. When vector x is not rotated, so whenever this happens, whenever we get ax is equal to some constant, the constant is in this case 5, so we got ax is equal to 5x. In general, we say whenever ax is equal to lambda x, ax is equal to lambda x for some constant lambda, then that lambda is eigenvalue and corresponding x is the eigenvector. Okay, so this is very simple definition of eigenvalue and eigenvector. So matrix multiplication becomes this, instead of multiplying the matrix, that become equivalent to a scalar multiplication. So whenever ax is equal to lambda x, we say the vector x is eigenvector and lambda is the eigenvalue. So come to the method here. So already we've seen the definition of eigenvalue and eigenvector. In a matrix equation, ax equal to lambda x, lambda is eigenvalue and x is eigenvector. Now, if we replace the vector x as a zero vector, suppose x is a zero vector, what happen? What happen? A into 0 is equal to lambda into 0. That means it obviously satisfies. So this is not a special vector then. Zero vector is not a special vector. So we are interested in non-zero vector. So we'll come to that also. So ax equal to lambda x can be written as ax minus lambda x is equal to 0. I taken this lambda x on the left hand side. So let I take x as a common. So we get a minus lambda of I of x to the 0. This I will come. The reason is there because it's matrix equation. In matrix equation, I is the identity element. So it is not like a number. So just 3 square plus 3 is there. Then we can take 3 into 3 plus 1. Why 1 is left there? Because 1 is multiplicative identity in a number. But in matrix, if we have a square plus a, and if we take a as a common, we left with a plus, it is not 1 now, it is a plus I. Okay, because I is the multiplicator. So same way this I comes here, this lambda is a number there. Okay, so what is my point here? The point is here, ax is equal to lambda x is the equation whose solution we want. We can convert that ax equal to lambda x in this form, a minus lambda I of x equal to 0. And now this is a system of homogeneous equation. It is in the form of like ax equal to 0, that form. Okay, system of homogeneous equation. We know, and we are not interested in zero vector, zero solution. We are not interested because zero is a trivial solution. We are interested in some special vectors which are non-zero vector, non-trivial vector. So to get a non-zero solution, we have a condition on the coefficient determinant, that determinant should be 0. For x equal to 0, we have non-zero solution if the coefficient determinant is 0. And because of that, we are solving determinant a minus lambda I to the 0. If we solve the coefficient determinant a minus lambda I to the 0, we get eigenvalues. And for each value of lambda, we solve the same equation for getting the eigenvector. So that about the two steps are there. Step number 1, always we get eigenvalue by equating the determinant a minus lambda I to the 0. This equation is also known as a characteristic equation of the matrix A. Okay, so by solving the characteristic equation of a matrix A, that is determinant a minus lambda I to the 0, we get eigenvalues. And for each value of lambda, we have to solve the matrix equation for the eigenvectors. Remember, if we have a square matrix of order 2, if we have a square matrix is of order 2, then we have 2 eigenvalues and 2 eigenvector. So 2 eigenvalues and 2 eigenvector. But if the matrix is of order 3, we have 3 eigenvalues and 3 eigenvectors. So number of eigenvalues and eigenvectors are equal to the order of that matrix. So for 2 by 2 matrix, we have 2 special values and 2 special direction. For 3 by 3 matrix, we have 3 special values and 3 special directions. Okay, so that is a theory. Now let we understand the same thing with the example. Suppose the question is here, find out the eigenvalues and eigenvector for this matrix A. So the method is very, very simple. Step 1, you should say step 1 is eigenvalues. Eigenvalues. We know for the eigenvalues, we always equate determinant a minus lambda I to the 0. So equate the determinant of a minus lambda I to the 0, we get determinant of, when we write a minus lambda I, remember this lambda into I. Okay, let I write first, then you will get under, then it will you will understand it better way. So the matrix A is minus 5, 2, 2, minus 2. This is matrix A minus lambda times the identity matrix is 1, 0, 0, 1. Is it? And this determinant should be 0. So this determinant now, this first matrix will remain as it is, minus 5, 2, 2, minus 2, minus, now when you take this is lambda 0, 0 lambda. And now we get a determinant. This lambda should be subtracted from, so subtraction of the two matrices. So it is a 5, minus 5, minus lambda, this 2 as it is, this 2 as it is, and minus 2, minus lambda. Remember, no need to show this step by step in the exam. For given matrix A, you can directly write this determinant a minus lambda I to the 0. After this step, you can write directly this. The middle, these two steps are not important. This is just for your understanding as shown. Now, our aim is to evaluate this determinant. So just cross multiply it. So you will observe minus 5 minus lambda, minus 5 minus lambda into minus 2 minus lambda, minus 4 equal to 0. Now, just multiply this bracket. So you get lambda square, say 2 lambda plus, that is 7 lambda, and plus 10 minus 4 is plus 6 equal to 0. So we get quadratic equation for lambda. Now we should factorize it and find out the roots of this equation. We get the eigenvalues. Remember, the best method to get the roots is a calculator method. The reason is, right now, yes, quadratic you can solve it by factorization also, but for cubic later on you can use a calculator method for getting the roots of this characteristic equation. So right now I can factorize it. It is a lambda plus 1 into lambda plus 6, that are the factors. So lambda becomes -1 and -6, and this is the end of the step 1. End of the step 1 means we have the eigenvalues -1 and -6 for the given matrix. Okay, -1 and -6 are the eigenvalues. Remember, there are few properties that you will learn later on. I will show it about the eigenvalues. So first property is sum of the eigenvalue. Sum of the eigenvalue is equal to sum of these eigenvalues is equal to the sum of a diagonal element. Sum of eigenvalue is always equal to the sum of diagonal element. In this case, it is -7 equal to -7. Okay, that is the first property. Second property says multiplication of eigenvalue is equal to the determinant A. So lambda 1 into lambda 2 -1 into -6 is a 6. Okay, so 6 is the multiplication, and if you evaluate a determinant, which is 5 twos are 10, 10 minus 4, that is 6 only. So that is a determinant A. So these are the properties just for MCQs. You can remember it. Sometimes it requires when you use a calculator method and there is a repeated root. To get that repeated root, you can use this sum of diagonal element is equal to sum of eigenvalues. Okay, this property. So that about step 1. The step 1 already I shown you. In the step 1, we got the eigenvalues which are -1 and -6, and the two important properties already I discussed. Sum of diagonal element is equal to sum of eigenvalues. Okay, sum of eigenvalues. Now, now the step 2. Okay, for the step 2, just I will go back again. Step 2, we can say step 2 is eigenvector. Step 2, eigenvector, and we should say consider matrix equation. Consider a minus lambda equal to this one. Consider a minus lambda of x equal to 0. So this is the matrix equation we got. So this is the equation number 1. For each value of lambda, we have to solve this equation 1. That gives us eigenvector. So I will say the case 1. Case 1, lambda is -1. We got -1 and -6, is it? So -1. If we replace -1 here, it is better you write down the equations only directly. So -5 plus 1, you get -4x1 plus 2x2 is equal to 0, because lambda is -1. We replace here -5 plus 1, -4x1 plus 2x2 is 0. Second equation, 2x1, 2x1, and here is a minus minus, so -x2. Remember, if you go by row echelon method, now if you find out the rank of the coefficient matrix, it always becomes a less than number of unknown. The reason is the coefficient determinant is a 0. That way only we calculated. So rank of the matrix is always less than number of unknown. So if you take like 2r2 minus r1, the second equation becomes a 0 equation. So take any equation, either take first equation or second equation, and create the relation between them. Or you just always start like assuming that x2 is a t. Let x2 is a t, replace in any of these equation number 1 or 2, we get x1 is equal to t by 2. Is it? So x2 is a t, x1 is t by 2. So our eigenvector x for lambda equal to -1 is, eigenvector x for lambda equal to -1 is, remember, the eigenvector is x1 is a t by 2, x1, this is the first component, x1 is a t by 2 and x2 is t. So this is the general eigenvector, but always we have to write down at least one non-zero eigenvector. So never put the value of t as a 0. So replace t by any non-zero value. The best value to replace in this case is this denominator. I will replace t by 2. So if t is a 2, so answer is 1, 2. 1, 2 is eigenvector. Remember, if I replace t by -2, if I replace t by -2, then the answer is a -1, -2. That is also the correct answer. So there are many possible answers: 1, 2, 2, 4, okay, 5, 10, -5, -10, and so on that way. So that about case 1. So we got for lambda equal to -1. Now we'll move to the case 2. I said case 2, lambda is a -6. For lambda equal to -6, if you replace in this one, so -5 plus 6 is x1 only, x1 minus, sorry, x1 plus 2x2 is a 0. That is the first equation, because -5 plus 6 is x1 plus 2x2. Second equation is a 2x1, and this -2, that is plus 4x2. And now Again, we can start with that way. Let x2 is a t. Let x2 is a t. Replace in any of this equation. Let I replace in the first equation. So my x1 will become minus 2t. Is that correct? So we're replacing in any of the equation there, and we get that infinitely many solutions. So in this case, the general eigenvector x1 is minus 2t and x2 is a t. So this is the general eigenvector, and I can write one particular eigenvector here by putting t equal to 1. So minus 2, 1 at t equal to 1. I put here t equal to 1. In the previous example, I replaced t by 2. So you can replace any value there. Don't worry. At least one vector we want in that direction only. So the direction is important. So or that line is important. You can put t equal to plus 1. You can put t equal to minus 1 also. But yes, you will get that eigenvector. And that is the end of a question. So step 1, we got eigenvalues which are minus 1 and minus 6. And step 2, we got the eigenvectors which are 1, 2 is eigenvector for lambda equal to minus 1. And minus 2 comma 1 is eigenvector for lambda equal to minus 6. So different student may have the different answers also. For example, if some other student write this eigenvector for lambda equal to minus 6, for example, he replace t is equal to say minus 4. T equal to let us replace minus 1 only. So that time 2 minus 1, 2 minus 1, because t equal to minus 1 replace. So this is also the correct eigenvector, 2 minus 1 or minus 2 1. Both are correct. So choice is yours. Okay, so that about the example 1, where we got eigenvalues in the step 1, and step 2 we got eigenvectors. For case 1, lambda is minus 1. We got eigenvector here. This is the 1, 2. And case 2 for minus 6, this is the eigenvector. So just I explained whatever the way I derived, that way you can do it. So 2 minus 1 or minus 2 comma 1, both are the correct answer, because when you multiply by minus 1 to that vector, the vector only sign changes there. Sign of the components will change. Example 2 is exactly similar to it. So I will just go through that. So this is the 2 by 2 matrix. We want eigenvalues and eigenvectors. So step number 1, we solve the determinant a minus lambda I to the 0, and we get lambda square plus 3 lambda plus 2 0. So if you factorize, lambda plus 2 into lambda plus 1 is 0. So lambda is minus 1 and minus 2. So these are the eigenvalues. Step 2, we solve a minus lambda of x to the 0 for each lambda. So when lambda is a minus 1, we get this equation. Let us put x2 equal to t. You get x1 is also t. So x1 equal to x2, that is t. So general vector is t comma t. If you replace t by minus 1, you get this vector. If you're not happy with minus 1, yes, you can replace t by plus 1 also. So the eigenvector can be minus 1 or 1 1 also correct. You have to write only one vector, but remember, do not write multiple vectors. It's not required. Either write 1 comma 1 or minus 1 comma minus 1. Similarly, for the case 2, when lambda is a minus 2, we get 2 comma 3 as an eigenvector. So just put x2 equal to t, find out x1, and then you can replace t by 3. You get that required answers there. Okay, choice is yours. Okay, so that about 2 by 2 matrix. Now we are moving to the next part here, and the next part is 3 by 3 matrix. So this is little lengthy example, because whenever we are given the matrix is of order 3 by 3, we get a cubic equation of a lambda, and we have to find out all the 3 roots of that cubic equation. Characteristic equation, that is a step 1, determinant a minus lambda is 0. This is a shortcut formula. Generally we prefer, because expansion of the determinant, you will waste too much time in the exam if you not remember this formula. So better, instead of expanding along first row, you should remember this shortcut formula. The formula says lambda cube minus sum of diagonal elements into lambda square plus sum of the minor of the diagonal element into lambda minus determinant a equal to 0. We'll discuss about the minor of the diagonal element. Okay, these are similar to the inverse by adjoint method. We require minors there. Okay, that's one only. So come to the example, it becomes more clear. So the question is, find the eigenvalues and eigenvector of this 3 by 3 matrix. So step number 1, we solve determinant a minus lambda I to the 0. But we'll not use now, we'll not use the expansion method, we use shortcut formula. We have formula lambda cube minus sum of a diagonal element. Now what is a diagonal element? 2, 2 and 2. Sum of diagonal element is 2 plus 2 plus 2. Sum of diagonal element into lambda square minus, not minus, plus minus alternate is there, plus, now plus sum of the minor of a diagonal element. Now if you want the minor of first diagonal element a11, if you want minor of the first diagonal element, just delete that column, delete that row, and we left with this part only. We have to take determinant of this. This is the m11 minor of a11, minor of the first diagonal element, which is 2 into 2 is 4 minus 0, so it is 4 only. So m11 is 4. Similarly, now if we want m22, what do we have to do? This is the minor of a22, we have to take minor of second diagonal element, ignore the column 2 and the row 2, and now this into this, 2 2s are 4, 4 minus 9, 4 minus 9 is a minus 5. So this is m22, minor of a second diagonal element. Now minor of the third diagonal element, which is a33, delete the third row, third column, and take the determinant of remaining. So it is a 4 minus 0, it is again 4, so 4. So these are the minors of diagonal element. This is minor of a11, a22 and a33. So into lambda is there. Minus determinant of a is there. Now to get the determinant, yes, we'll expand it along the first row. So what is that expansion? This 2 into its minor, so 2 into 4 minus 0 into its minor, so no need, plus 3 into its minor, that is a 0, minus 6 equal to 0. So this is the simplest method to get a cubic equation. See, this is the lambda cube, sum of diagonal element, this is sum of a minor of a diagonal element, and this is the determinant value. If we simplify, we get a cubic equation, lambda cube minus 6 lambda square. This is a 4 plus 4 is 8, 8 minus 5 is a 3, so 3 lambda, and lastly this is 8 minus 18, 8 minus 18 is a minus 10, minus plus 10. Now another important thing comes here, how to get the roots of this one. Already I told the best method is a calculator method. So just use a scientific calculator now. Take a scientific calculator, press mode button of your calculator, press roughly 3 times, you will get equation mode. So press 1. Now calculator will show you the number of unknowns. Number of unknowns is 2 or 3. That is not our case because we are not solving system of equation. Okay, we have cubic equation. So just press right arrow of the top side there. So if you press right arrow, it shows you the degree 2 and 3. So it is a cubic equation. So I will press 3. If I press 3, it is a cubic equation, and this cubic equation is like this: a lambda cube plus b lambda square plus c lambda plus d equal to 0. So these are a, b, c and d values. So what is a here? A is 1. So if I press, then just press 1 and equal button. So the value of a is fed as 1. Now it gives you b question mark. So b question mark means it is minus 6 now. So press minus 6 and equal. Then c question mark, that is 3 equal. And lastly d question mark, that is a 10 equal. Now calculator will give x1 is a 5. X1 is a 5. Then again press that button. So minus 1 and 2. So 5 minus 1 2, these are the eigenvalues. 5 minus 1 2. So you can write down directly lambda is 5 minus 1 and 2. So these are our eigenvalues. That is the end of the step 1. Okay, so 5 minus 1 2. Now how to cross check whether our values are correct or not? Sum of eigenvalue is equal to sum of diagonal element. 5 plus 2 is a 7, minus 1 is 6, and sum of diagonal is also 6. So yes, our eigenvalues are correct. So this is just an idea or just a confirmation whether we got the correct values. So that about the end of the step 1. We got the eigenvalues. We got eigenvalues by using a shortcut formula, which is a lambda cube minus sum of diagonal element into lambda square, and so on there. Okay, that way. Come to the step 2. Step 2, eigenvector. For each value of lambda, we have to solve this matrix equation. What is that matrix equation here? 2 minus lambda, 0, 3, 1, 2 minus lambda, 0, 3, 0, 2 minus lambda of x means it is three-dimensional vector x1, x2, x3. So this is the system we have to solve it for each value of lambda. So I'll start here as a case 1. Case 1, lambda is 5. Lambda is 5. So remember, already we know for each value of lambda, the rank of the coefficient matrix is always less than number of unknowns, so that we get a non-zero vector. So just write any two equations from this system which we have to solve it there. So the first equation for lambda equal to 5 is 2 minus 5 is it minus 3? Minus 3x1, 0x2 and 3x3. Second equation is x1, 2 minus 5 is a minus 3, minus 3x2 and 0x3 equal to 0. Remember, you can write third equation also, and you can solve that system of equation by row echelon method. By row echelon method also you can solve it. Choice is yours. At the end you have to find out that infinite solution. Okay, so write the third equation as 3x1 plus 0x2 minus 3x3 equal to 0, and solve by row echelon method. That is one of the way. I'm going to get the answer by Cramer's rule here, because the Cramer's rule is the simplest method when we know there is infinite solution. And the Cramer's rule for the system of two equations for three unknowns is solved like this. We have to write it. Say first variable is x1 upon a determinant. Now what determinant do I have to take it? The coefficient of x2 and x3. What are the coefficient of x2? 0 minus 3, 0 minus 3, 3, 0. This is x1 upon, equal to minus of x2 upon determinant. Now the coefficient of x1 minus 3, 1, 3, 0. So these are coefficient of x1 and x3. Now middle term have the minus sign, remember this. And x3 upon the determinant, now coefficient of x1 and x2. x1 coefficient are minus 3, 1, 0, minus 3, 0, minus of 3, and is equal to t. You have to take that parameter now, because we have infinite solution. So each ratio is equal to the parameter t. And now we can easily get, see this determinant value, this is 0, minus 9. So what is x1? x1 becomes x1 equal to minus 90. Is it correct? x1 is minus of 90, because you are cross multiplying. So this is 0 minus 9. x1 upon minus 9 is there. So x1 is minus 90. Now this case, this is a 0. This is minus 3. So minus x2 upon minus 3 means x2 is a 3t. x2 is a 3t. And the last one, x3, this is a minus 3 into minus 3 is a 9. So x3 is also 90. x3 is a 90. So we got a general vector x, which is x1, x2, x3. x1, x2, x3, that way. So we want some particular vector. So you can put t equal to 1. If you put t equal to 1, we get one vector minus 9, 3, 9 is an eigenvector. So this is the end of a question. We got eigenvector minus 9, 3, 9 for lambda equal to 5 at t equal to 1. If you are not happy with the t equal to 1, yes, you can make its smaller magnitude by putting t equal to 1 by 3 also. If you put t by 1 by 3, your vector become minus 3, 1, 3. So minus 9, 3, 9 or minus 3, 1, 3 is also the correct answer. Is that clear? So that about case 1. Just we completed case 1. Lambda is a 5. We have to do this same thing for lambda equal to minus 2 and lambda equal to 2 both. Okay. So I will show you one more, say minus 1, and you can take the lambda equal to 2 as self-study. Okay, you can do it your own. I will show you the answers, but okay, don't worry. So case 2, I am going to do it. So for the case 2, we have to put the method remains same, everything is the same, only just a minute, I have to erase it. Okay, so this is the matrix equation a minus lambda, and case 2 we're starting the case 2. Say lambda is a minus 1. So by 1 in this we are putting lambda by minus 1. So 2 plus 1 is a 3, 3x1 plus 0x2 plus 3x3 is a 0. Next, x1 plus 3x2 plus 0x3 is a 0. I taken only two equation because I'm going to use a Cramer's rule again. So for a Cramer's rule, the method is x1 upon, it's a determinant now. The determinant is in this case 0, 3, 3, 0 minus x2 upon a determinant, in this case 3, 1, 3, 0, and lastly x3 upon a determinant 3, 1, 0, 3, and is equal to t. What about x1? X1 equal to, you'll observe this is 0 minus 9, so minus 9t only, similar to the previous. X2 equal to, this is a 0, this is minus 3, so x3 is this minus minus plus, x3 is a 3t, and x3 now last 9, 9t, and now our eigenvector x is minus 9, 3, 9, minus 3, minus 9, 3, 9 is the eigenvector for lambda equal to minus 1 at t equal to 1. At t equal to 1. So this is a way, yes, you can get it. I will just show you all these calculation, directly the answers. Step 1, already I told, you should find out the lambdas there, which are 2, 5, minus 1. So for 2, 5, and minus 1, you will observe the vectors written 3, 1, 3 or 9, 3, 9, minus 9, okay, minus 9, 3, 9 also. So multiple ways are you can write it, and here is a 0, 1, 0 you will get. Okay, you can try your calculation, just take any two equation. In that case, remember directly last equation gives us 3x3 is a 0, so x3 is a 0. Similarly, first equation gives us, first equation gives 0x1 plus 0x2 plus 3x3 0, so x3 is a 0. Last equation gives you 3x1 plus 0x2 plus 0x3, so x1 is a 0. So x1 and x3 are 0. So obviously you can take first and second equation also. Any two equation you can take, you get x1 and x3 0. So x2 is left only. So x2 left, so you take x2 equal to t here. So for this lambda equal to 2, actually your let x2 is a t, because we do not have equation for x2. And so x2 is taken as t equal to 1 is taken. So you get 1, 0, 1, 0 is a vector there. Okay, so that way we got an eigenvector here. This is the simple question that you have for 3 by 3. So that about example 3. So 3 by 3 examples are really, really lengthy examples. But yes, there is no difficulty actually. These are lengthy only. So there is some similar process that you can use it and you can get. So this is another example where you are given 3 by 3 matrix. So step number 1, we should solve determinant a minus lambda to the 0. And if we solve this determinant a minus lambda to the 0, the directly that shortcut formula, lambda cube plus sum of diagonal element is a 7 into lambda square plus sum of minor of diagonal element is a 15, and minus determinant is a minus 9 there. So you'll get this equation. So you are taking from this one only. So this is a cubic equation, you'll get it. Now here, if you use a calculator method, now just use a calculator method and try it. First you clear your mode, whatever you've done, shift clear and press 3, or everything will be clear there. Okay, now press mode again, come to the equation mode 1, right arrow, degree is a 3, and if you put the values of a, b, c, d, that values, a is a 1 here, so I press 1, b is a 7, c is a 15, and d is 9. The calculator will show you x1 is minus 1, x2 is minus 3, okay, x1 means lambda is a -1 and -3. Now what is the change that I want to tell you here? Lambda is a -1 and -3. These are the roots given by a calculator. Now calculator will not show you which root is repeated, because this is the 3 by 3 matrix. It will have 3 roots. So maybe -1 is repeated or -3 is repeated. Suppose -1 is repeated, then what will be a pair? -1, -1, -3. But there is other possibility also, that -3 is repeated, then roots will be -1, -3, -3. Now which one is correct? So obviously, how to check? We know the sum of diagonal element. Sum of diagonal element is equal to sum of eigenvalue. What is the sum of diagonal element? -14 plus 7, -7. -7 is the sum of diagonal element. So where is the sum -7? This sum is a -5. This is -7. So this is a correct root. So what we can say? Therefore lambda equal to -1, -3, -3. This you have to write it directly. Okay, use a calculator, but decide which is a repeated root by using the property sum of diagonal element is equal to the sum of eigenvalues. So our roots are -1, -3, and -3. Now what happens? Only two cases will become. We have to solve this matrix equation a minus lambda I of x0. A minus lambda I of x0, you have to solve it for -1 and -3 only. Okay, so let me check what will happen. -1 and -3, these are the eigenvalues. Remember, -3 is a repeated root. That is again a special thing that you will observe what will happen for this. So just I will come to that part only. So this is the matrix equation a minus lambda I of x equal to 0, and we are moving to the case 2. Case 2, lambda is -1 and -3. So -1, lambda equal to -1 is not new. Just like a previous example only, you will get it. When you put lambda equal to -1, what happens? The first equation becomes 7 plus 1 is 8, 8x1. Next equation becomes -2x2. Third coefficient is -4, 14x3 equal to 0. Second equation comes, say 5x1, and here is a -1, so -3x2, and last is -7x3 is a 0. I will take one more. Yes, two equations are enough. There is not a problem. With these two equations, you can find out because it is a non-repeated root. So just two equations are enough to get x1, x2, x3 in terms of a t. Use a Cramer's rule. Say x1 upon the determinant, which is -2, -3, -14, -7. That will to -x2 upon the determinant, -x2 upon, so 8, 5, -14, -7, and x3 upon the determinant, and that determinant is 8, 5, -2, -3 is equal to t. We are saying. So this will give us x1 equal to, you will observe, solve this determinant now. This plus 14, and 14 threes are, just 1 minute. So 14 threes are 42. So that is a -42, plus 14. So it is 28, is it? This is a plus 14 minus 42. So it is a 28, but it is a minus 28. So minus 28t. X1 is minus 28t. Come to the x2 now. X2 equal to, remember there is numerator, I have this minus sign. So this is 56, and this is minus 56, and this is plus 70. 56 and 70. So is it 14? So 14t. Sorry, this minus sign will come on that side. So minus 14t. Numerator of the minus sign. So this plus 56. Sorry, minus 56 plus 70. So plus 14. Minus 14 will go on the other side. And lastly, x3 equal to. So this is a 24 minus 24 plus 10. It is a minus 14 again. minus 14t. So our eigenvector x will be, in particular, if you put t equal to 1, it will be minus 28, minus 14, minus 14, or if you put t is equal to 1 by 14, or let us put t equal to, if you put t equal to minus 1 upon 14, minus 1 upon 14, the simplest eigenvector will become as, if you put t equal to minus 1 upon 14, everything will become plus, it will become 2 1 1. 2 1 1 is the eigenvector for lambda equal to minus 1. 2 1 1 is a simplified eigenvector. This is also correct. By chance, if you write this one, it's okay, but I generally suggest you write simple vector, that is okay. So 2 1 1. So the case 1 is very simple, for lambda equal to minus 1. Again, by Cramer's rule, we solved it. Case 2 is also simple, but there is some special thing that I want to tell you. So case 2, our lambda is minus 3. Lambda is minus 3. Now what happens in such a case? Remember, when there is a repeated root, you no need to write two equations. One equation is also enough. If you see, because all three equations become same. All the three equations become same for the repeated root. See, lambda equal to minus 3. First equation, 7 plus 3 is, na? So minus minus plus. So 10x1 minus 2x2 minus 14x3 is a 0. That is the first equation, is it? Second equation, 5x1, this is a plus 3, so minus x2 minus 7x3, 0. Third equation, 5x1 minus x2 minus 7x3 is a 0. What happens? Equation number 1, 2 and 3 all are same actually. First is only 2 times of these last two. So just you left only one equation now. You have to just, whenever it is a repeated root, take any one equation. And here we get infinite solution in terms of two parameter. So let us assume x3 is a t1, x3 is a t1 and x2 as a t2. Then x1 will become, see, x2 is a t2, so this t2 plus 7t1 upon 5. So the vector is x1 x2 x3. Now as minus 3 is a repeated root, this is the some new thing now. Minus 3 is a repeated root. We have to write down two eigenvectors for repeated root, because there should be a three special vector. Now these eigenvectors we can write it by putting t1 equal to 1 and t2 by 0. If I put t1 1, t2 0, I get one vector. See, t2 is a 0, this is 0. And say now to remove this fractional part, I can put t1 equal to 5 also. If I put t1 equal to 5, that 5 gets cancelled. So I'll put t1 is a 5 and t2 0. What happens? See, this 5 gets cancelled, so x1 becomes 7. Okay, this is 7 because t1 is 5 and t2 is a 0. So t2 is 0 means x2 is a 0. And what about t1? T1 is a 5. So this is one eigenvector. This one eigenvector we got for 5 and 0. I can write one more vector here, x, for say now t1 is a 0. If t1 is a 0, we put t2 as a 5 now. T2 as a 5. So t2 is a 5. So what about x3? X3 is 5 by 5. Am I written correct? Yes, correct. So x1 becomes, so 5 by 5 is 1. That is 1. Now x2, t2 is a 5, so it is 5 and 0. Now the question may comes in your mind, why we are putting 1 0 and other as a non-zero? Because there is one important property of eigenvectors, that eigenvectors are linearly independent. And whenever we do this way, whenever we get a solution in terms of two parameter t1 and t2, in such a case we have to replace one as a 0, other as a non-zero, like t1 5, t2 0, t1 0, t2 5. In that way, whatever the vectors we get, they are linearly independent vector. To fulfill that property, we are doing this. So for lambda equal to minus 3, these are the two eigenvectors. So whenever repeated root is there, always there are two eigenvectors. So that is the special case that I want to show you. And here are the solutions. So this is already done. So I shown you that minus 3, minus 1 is a eigenvalues. Minus 3 is a repeated root Because of that, we have these two eigenvectors. So two eigenvectors for that repeated, and how we got? By putting 1 0, other non-zero, that way. So 0 5 5 0. This is the way you can get it. And this is actually 2 1 1 can be get for lambda equal to -1. So this x3 is for -1. So this is the way we can get eigenvalues and eigenvector. So that are the things we have. So there are few more examples are there. This is just for practice. Do it your own. Check. This is the matrix you are given. Solve the write that cubic equation. Do not go in the factorization method. Just take that lambda cube minus sum of diagonal element. You will get these eigenvalues. For each of the eigenvalues, solve the system of equation. When it is non-repeated root, solve by Cramer's rule. You will get these eigenvector. Okay, take it like a self-study. Do it your own. So, okay, do that calculation. And here are the properties of eigenvalues, which we already used. Sum of eigenvalues is equal to sum of diagonal element. That is one property. Product of the eigenvalues is a determinant A. Remember, the matrix A and the transpose matrix have the same eigenvalues. So if you calculate, if you have the eigenvalues of the matrix A, remember the transpose also have the same eigenvalues. Suppose lambda is eigenvalue of the matrix A, then 1 by lambda is the eigenvalue of A inverse, that is 1 upon A. So actually A inverse. Okay, so A inverse have the eigenvalue 1 by lambda. If lambda 1, lambda 2 are the eigenvalues of the matrix A, then lambda 1 raised to m is the eigenvalue of A raised to m. Okay, so this is just power there. And if lambda is the eigenvalue of the matrix A, then k lambda is the eigenvalue of the matrix K into A. And these are the simple properties and most important property that we use there, that all the eigenvectors are linearly independent vector. Okay, eigenvectors are linearly independent. So these are just for your knowledge. Maximum MCQs will come on this. So if MCQ is there, you should able to answer it. And this is the last example. Provided if we know the eigenvalues and eigenvectors of the matrix A, you can write the eigenvalues and eigenvector of these matrices easily. Remember, when the lambda 1 and lambda 2 are the eigenvalues of the matrix A, then lambda 1 square and lambda 2 square are of A square there. 1 upon lambda 1, 1 upon lambda 2 are of A inverse. And this is also you can get it. I will show you. That is lambda 1 plus 4, lambda 2 plus 4, that way. But eigenvectors will be the same. Eigenvectors of the matrix A as well of all these matrices are the same. So eigenvectors never change. Okay. So if you do it, you will get 1 1, and these are the eigenvectors. These eigenvectors are for all the matrices: matrix A, A square, A inverse, and everyone. But A square will have the eigenvalue because A have the 1 and 3 eigenvalues. So A square have 1 square and 3 square. A inverse has 1 upon 1 and 1 by 3. A plus 4i, 1 plus 4. So these are the eigenvalues of the other matrices. Okay. So because of the properties, we can easily write these eigenvalues. This is just, again, this is not so important example, last question. But yes, you should know. If you know the eigenvalues and eigenvector of the matrix A, you can find out the eigenvalues and eigenvectors of its other matrices which are obtained from them only, like by squaring, reciprocal, or addition way. Okay, so it is one of the important article, lengthy article, but yes, the two things are there only. Step 1, eigenvalues by equating determinant to the 0. Step 2, for each value of lambda, solve the matrix equation. So that about your second last article of your syllabus, eigenvalues and eigenvector. Thank you.